We are beginning our conversation of waves, and this is actually going to include more than one chapter. So I want to give you a brief overview so that you can better understand what we're talking about now and how we're going to be continuing this into future weeks. So first, we can categorize waves in a lot of different ways, and there's going to be two bifurcations I'm going to be talking about here. So one of the ways to categorize waves is traveling versus standing. And traveling waves are what we're talking about right now. Standing waves are going to be a special situation that we talk about, largely involving, for instance, musical instruments and sound. So we're not actually going to talk about standing waves in this chapter, but it's something you're going to see in a later chapter, and it requires understanding something about this chapter. So the next thing to understand is mechanical versus electromagnetic. So mechanical waves are basically all waves that travel in a medium, and we will soon define what that means. And electromagnetic waves are actually special. In this chapter, at least initially, we are going to be focused on mechanical waves. We will meet electromagnetic waves later in this chapter, and then we're going to see it later in a different chapter going back after what we studied with electricity and magnetism. So you might think that, hey, why aren't we talking about electromagnetic waves given that we just talked about electricity and magnetism? We're going to focus on mechanical waves, like a wave on a string or a wave on water, to think about the basics first. Then lastly, one of the ways that we can categorize waves is either transverse versus or longitudinal. And we are going to be talking about both of these initially. So transverse is easier. Longitudinal is a little harder to understand. So when we talk about longitudinal, this is largely going to be related to sound. And so whenever we're not talking about sound, we'll be talking about transverse waves. And many of the things we'll talk about will then be expanded to longitudinal. So again, sound is going to be a big topic, and it's largely going to be our standing waves and our longitudinal waves. So for instance, a traveling wave can be transverse or longitudinal, and mechanical waves include both transverse and longitudinal. So there's overlap between these different categories. So hopefully that gives you some idea. Again, transverse and longitudinal we are talking about right now, so we will clarify the distinction between those right away. So a transverse wave is the easiest thing to think about in that the wave is traveling to the side, right? So notice that we have a side travel here, but that the motion itself, or the place where you see the wave, is up and down. So effectively you take your hand and you jerk your hand up and bring it back down, which then creates a pulse which travels across the screen. So again, it's difficult for me to actually show you any sort of animation here. But so we're going to be talking about the idea of displacement. And in this case, displacement is up and down, but then again, that motion is to the side. So we have a lot of different ideas to think about. And in this case, we're talking about a pulse. So when we talk about a pulse, we can still talk about motion and displacement. And if you remember, a long time ago, at the beginning of intro mechanics, displacement was a difference in position. So it was a vector. In this case, displacement has a slightly different meaning. So the other term that isn't labeled here but is important to think about is equilibrium, right? If I hadn't actually shaken my string, this blue line here would represent equilibrium. Now, you might think, well, hey, if one end of the string is just tied off, I think the string would actually sag a little bit under its own weight. And you're right, and a simplification we typically make is that equilibrium would be a straight line. So in this model, we're not actually thinking about gravity at all. So this sort of wave motion would still work, for instance, if you were in deep space away from any sort of gravity. So the important part of a transverse wave is, again, that the displacement is one direction, say vertical in this case, but then the motion is horizontal. So for transverse, the displacement is perpendicular to the motion itself. And so when we talk about longitudinal waves, that's going to be the primary distinction. So a longitudinal wave, we need to think, for instance, about a slinky. So now the displacement is actually horizontal, and we can, for instance, be pushing or pulling the end of the slinky, but the motion is then also traveling in the same direction. So we have horizontal pushing and pulling, which means a horizontal displacement, and the motion is also horizontal. So what the displacement in this case corresponds to, notice that we have some particles here, right? So these black dots represent certain spots, and it can be helpful to think through that. But notice that in some places there's a certain spacing, but then here it's crunched together, and here it's actually a little more spread out. So this is like we actually pushed it together, we compressed the slinky, and that is what is traveling. And in order for it to be pushed together here, it actually has to be spread out more there. So that's the basic idea of a longitudinal wave. The only longitudinal waves we'll really talk about are like this, when you have a slinky, a coil that can actually have compressed areas, and then these what's going to be called a rarefaction, but an opposite of compressed area. Another example is going to be sound. So again, when we talk about sound, we need to talk about longitudinal waves, but this is obviously a little harder to think about since we don't directly see the wave. We do as we in the transverse case. So transverse waves will be easier, so we're really going to start thinking about that. So one of the things we have to understand when we're talking about a wave is some of the terminology. And one important thing to think about is the medium, and we'll frequently be talking about a disturbance of a medium. So the disturbance itself is, in a way, the wave, right? So think about this pulse here that you can see traveling on a slinky. So the pulse is traveling to the right, and the speed that that pulse is traveling would be the wave speed. And so this is like T1, we have this later picture here, T2, T3, T4. So you can see there's some delta x over a change in time, so we have a speed. But it isn't that the entire slinky is being thrown to the side, right? So this is the difference. The medium is, for instance, the slinky. I can pick up a slinky and I can throw it at someone. I can, for instance, throw it down the stairs. And that is then an object that has a speed. In this case, the slinky is effectively at rest, but it is the disturbance that is moving. But the disturbance has to move in something, and that something is the medium. So in this case, the slinky is the medium, the wave is really this disturbance, which is the pulse, and the pulse is traveling to the side with a certain wave speed, which is not the overall speed of the slinky, because the slinky is really just sitting there, mostly. So another example is the wave at a sporting event. Now this might be something you're familiar with. If not, we can try to demonstrate it, but it really only works well in big groups of people. And the idea being that you have a big arena where most everyone is sitting down. But there's one region where the people stand up, but then what happens is if we, for instance, say that the wave is traveling this way, these people are starting to stand up if they're doing it right, but then these people are starting to sit down. So each individual person only stands up or sits down. They don't suddenly run to the side, but we actually see this disturbance move, and we would talk about that being the wave speed. And this disturbance can actually go very, very fast in the arena, faster than you could just run. So again, we have to think about the medium, which here is actually the people. The disturbance is them standing up and down, which then propagates to the side, if they do it right, at a given wave speed. So we're going to keep going through examples of this, which will hopefully make it more clear. Right now we are talking about traveling waves. We're not talking about standing waves. So again, we'll come back to standing waves in a later chapter. An example of a traveling wave is imagining having a rock dropped into a pond. we then see these ripples that spread outwards. Again, it isn't that the entire lake is moving away from this, it's just that the ripple is moving on the surface. So the ripple is the disturbance, the water is the medium. And again, the water really is just going up and down more or less in place, but the ripples are actually going to the side. And if we watch the ripple, it would have a well-defined speed, which is the wave speed. So what are some examples of wave speeds? First, it's important to recognize that the wave speed is a property of the medium. So later we're going to talk about other properties of waves, but the wave speed is determined by what the wave is in. So for instance, if we're talking about a string, the wave speed is given by tension, so T stands for tension, and on the bottom is mu, and this is going to be the mass per length of the string. Section 4 of this chapter does the derivation of this, and we're not really going to worry about the derivation of where this comes from. But you can see that a thicker versus a thinner string, or a steel string versus a cotton string, are going to have different speeds. A very taut string with high tension is going to have a different speed than a very loose string. So the string isn't the wave, the string is the medium. And depending on the properties of the string, which is the medium, you get a different wave speed. Sound has a speed of 343 meters per second in air at 20 degrees Celsius. This doesn't depend on the frequency of the sound. A high-pitched sound versus a low-pitched sound will all travel at the same speed. But if the air is hotter or more or less humid, that will actually change the speed. Lastly, electromagnetic waves, and we have talked about this already, have a fixed speed, which we typically call c, which is 3 times 10 to the 8 meters per second. So obviously this is very, very fast. The speed on a string is typically going to be less than the speed of sound, unless we're talking about sound in a string. So this might be maybe tens of meters per second or less. So you can see that we're talking about different orders of magnitude here.